Hello and welcome to Mr. Limford's Math 097 course. This is a discussion of section 2.2 of the notes. The topics we're going to discuss in this section are about slope, the slope formula, and parallel and perpendicular lines. And in particular, we're going to look at how we can study the slopes of these two sets of lines. Now starting off with the notes, let's remind ourselves what exactly is slope. Oftentimes, slope is considered the steepness of a line. Or sometimes a common way of saying it is people will say slope is the change in y over the change in the x. But let's remind ourselves there are a couple different types of slopes. Now, when working with slope, the big idea here is we are in fact looking at the steepness of a line. But we're looking at it in a couple different ways. We're looking at it almost directionally. So if I had a line like this, as I move left to right, we're going upwards, we're increasing. So this is a positive slope. As we move left to right for this line, it's going down, so that's a negative slope. Now if I was to move left to right and I stayed at this flat horizontal line, that's going to be a zero slope. And if my line was purely vertical, straight up and down, this would be called undefined. And let's see if we can figure out by the end of this video why this particular slope right here is 0, while this one is undefined. Now, the definition that we're going to use for slope is we're going to keep it incredibly mathematical. M, that's what we call slope, is the change in y over the change in x. Now, really quick, I'm going to be using this symbol. This is a triangle. It's called delta. This is a Greek symbol delta, and it just means change. You might see this in science class, like the change in temperature or something. So, slope we're going to define as the change in y over the change in x. How much am I increasing in my height or decreasing in my height, and how much am I moving over left to right? So if I were to plot 2 points, I'm going to plot a point right here at the origin, and let's plot a point right here. So that's at 0, 0, and this is at 2, 1, 2, 3, 4. All right, so I got a point there and a point at 0, 0. Now, to study the slope of the line that goes between these 2 points, I'm going to try to draw this as straight as possible. Yeah, totally missed that one. Close enough. So if I was to study the slope of this line, to come up with an actual number, an actual value for how steep it is, we look at how much is it increasing. Well, to go from this point to the height of this point, I have to go up 4 units. And then I look at how much is it going left to right. Well, to get from here to as far right as this point, I got to go over 2. Sometimes this is kind of thought of as like the game of Battleship, or if people are walking different blocks to get to a different location, you got to go up 4 units and then over to the right 2 to get to the next point on the line. So this slope, the slope of this line is going to be 4 over 2. I changed 4 units in the height and 2 units in the left and right direction. So that's my slope, and in fact we can simplify this slope to be 2 over 1. And take a look here. That means if I go up 2 units, let me see if I can do this in a different color. If we go up 2 units and over 1, hey, I'm at another point on the line. So this is an important idea that we are kind of discovering here. Slope really is a constant value, but it can be written a little differently. Slope could be, for example, 4 over 2, it could be 2 over 1, it could be 16 over 8, any kind of multiple like this. So when we work with slope, we want to have the minimum, the most simplified fraction possible, and that's what's going to be the value for our slope. Now, slope can come in a variety of forms. One way we can look at it is in the physical sense. Now, in the physical sense, this means real world. Real world. And this is, imagine a ramp or a steep hill or something you can actually physically see in the real world, something that we can actually measure as a steepness. Now in this case, let's imagine we got a ramp here and we got this little skateboarder going down the ramp. And this ramp, let's say it starts with a height of 3 and it's 8 feet long. So this isn't that big of a ramp, right? We're only 3 feet in the air. It's about 8 feet long. But let's say we wanted to measure the steepness of it. This slope would be 3 over 8. We are 3 feet up and we are 8 feet horizontally. Now let's say that we wanted to build an even bigger ramp because we're getting more dangerous, we're getting more daring. So what if I wanted to just double the size of this ramp? So right now, let's say I made a new ramp and I made it 6 feet tall and 16 feet long. I just doubled the size of it. The slope of this ramp, let's see, what's that going to be? 6 over 16. Which of these two ramps, the first or the second one, which of these two ramps do you think is steeper? Pause the video, take a minute, look at the two slopes, and determine which one's steeper, the bigger or smaller ramp. All right, well, hopefully you were able to pause the video and think about this, but it should be pretty obvious. If I were to take this line, or this slope, and I were to simplify it, I could divide 2 out of the top and 2 out of the bottom. What do you know? We get right back to the exact same slope as before. It turns out that these two ramps, though one's bigger than the other, they have the same steepness. So the slope of something doesn't really matter about the size of the object, whether it be a ramp or a hill or whatever. It's all about what's its angle, how much is it increasing over time, and they're increasing at the same rate. So another thing we want to do when thinking about slope is discussing slope that's what's called functional slope, and this is abstract. Now, abstract is a term meaning not really in the real world. It's not a concrete, realistic idea. So, for example, this graph right here talks about the depreciation of the iPhone 6 over time. Now, the iPhone 6 started depreciating value as soon as the iPhone 7 came out. And it's kind of hard to see here, but this is week 0. This is when the iPhone 7 came out. And this right here is week 25. So that's 25 weeks after the iPhones come out. Look at how huge of a drop this is. Look at how much my phone is losing value. As soon as the new model comes out, this is how much that phone was losing value. Well, here's the problem. I can't actually physically see my phone lose value. I can't see this relationship, right? It's an abstract idea. It's something that we came up with. So if I wanted to know how quickly something is changing, if I wanted to know the steepness of this line, what I'm really asking is, how quickly is this changing? At what rate am I losing money? At what rate is the value of my phone changing? So that's why when we typically look at slope here, we call it the rate of change. The rate of change is really just a fancy way of saying slope. However, in this case, it's kind of obvious what we're looking at. I don't want to measure how steep the line is for any physical sense. I want to measure how steep the line is to know at what rate am I losing money. Now, when we talk about slope, it helps us to know about a way to actually go ahead and calculate it. Because I don't want to have to just look at this graph. I mean, this is kind of a tiny graph. It's kind of hard to see if the points weren't labeled. I want to know an exact formula for calculating slope. Now, that formula says that if you are given 2 points on the line, you can plug them into this formula by subtracting the 2 y values, subtracting the 2 x values, and you'll have your slope. So let's take a look at a practice problem and see if we can implement this formula. In this first practice problem, we have the point 60 and the point 43. The very first thing I want you to do is I want you to pick one of these points to be point 1 and one of these points to be point 2. It doesn't matter which you pick, so I'm just going to say that's point 2 and that's point 1, whatever. So I'm going to say that the slope of this line is, well, let me take the y value of the second point. So that's a 3. And let me subtract the y value of the first point. Well, that's 0. Now let me take the x value of the second point, that's 4, and subtract the x value of the first point, that's 6. If you need to, pause the video and remind yourself that if 6, 0 is 0.1, then that's the first x point and that's the first y point. And if the point 4, 3 is 0.2, that's the second x point and that is the second y point. So this is the formula we're sticking with. It doesn't matter which coordinate point you pick to be 0.1 and 0.2. However, and pay attention to this, however, once you pick which one you want to be 0.1 and which one you want to be 0.2, you cannot change. I cannot do this. Okay, I'm going to say 3 minus 0, and then I'm going to say 6 minus 4. See how I changed these around? I moved around these x values. I get a totally different answer. I get 3 over 2, okay? When I should really get negative 3 over 2, okay? So this is why this is such an issue, because it gives you a totally different value. So let me try and get this off here. So we want to stick with just figuring out what our slope is and sticking with those points. Let's try another one. Pause the video. Give yourself a chance to do practice problem 2. But we're going to start with it right away. I'm going to say, again, that's 0.2, that's 0.1. Doesn't really matter. But 3 minus 2 over 4 minus 1, that is just 1/3. Okay, so I got my slope there. This is pretty easy. This isn't that bad, is it? I actually kind of like some of these problems because after a while, they just kind of become like Zen almost. You're just kind of plugging stuff in and calculating. The number one error I see students make are where they swap points, like right here. They pick something for 0.1 and 0.2, and then they just swap and move things around. Just don't do that. Just be careful. I like to label what my points are, so I'll label that's 1 and that's 2, just so I don't get confused. Now in this problem, I subtracted 3 minus 3. I'm going to get 0 over 2. This slope is just 0. That's a terrible 0. There we go. That's a 0. So this slope should be just a straight up horizontal line. That's what I'm anticipating with this. Now, I'm going to skip over this application problem because we're going to be doing it a little bit later. But what we want to talk about right now are parallel and perpendicular lines. You should have a grasp of how to calculate slope. Now what we want to do is we want to be able to determine the relationships between lines based on their slopes. Parallel lines. These are lines that never intersect. Lines that never intersect. So they should be two straight lines going off in the same direction and never intersecting. On the other hand, perpendicular lines are lines that, and I'm going to say cross, lines that cross or intersect at 90-degree angles. So I'm going to try to draw as best I can something like this. So you can see these two lines, they're intersecting at 90-degree angles. This is what it means to be perpendicular. Now, what's unique about this are the slopes to these lines. If two lines are parallel, then their slopes are the exact same number. The slope of line 1 is the same thing as slope of line 2. That's it. They are the exact same. Now, if they're perpendicular, going to be a little different. If you have two perpendicular lines, the slope of one is the negative reciprocal of the other. So what does that mean? Let's do a quick little example problem. If you're trying to find the slope of a line, and we're going to say it's perpendicular to, let's say it's perpendicular to 1/3. And I want, actually, no, let's make it 4/3. And I want to find a line perpendicular to this. So a perpendicular slope to 4/3 is negative 3/4. I change the sign and I flip the fraction. That's what it means to be a negative reciprocal. Let's do another example. Let's take 5/2. The perpendicular slope will be, let's see, I gotta flip it, so it becomes 2/5, and I have to make it negative. So, -2/5. Some kind of more weird examples. What would 3 be? What would the perpendicular slope be for the number 3? Well, remember 3, there's an imaginary 1 underneath it. All whole numbers are over 1. So if I wanted to flip that into a fraction and become 1/3, and I got to make it negative. Nothing wrong with that. That's pretty straightforward. What if I gave you a negative 2/7? How about a negative 2/7? What would the perpendicular slope be for this? Well, we're going to have to flip it to be a reciprocal, and then I'm going to switch the sign to be positive. So there we go. That's how you're finding perpendicular slopes. You're flipping the fraction, and you're changing the sign. That's it. It's pretty straightforward as that goes. Now, we're going to be using this idea of parallel and perpendicular lines going forward in the next section when we actually go about writing equations. So be comfortable working with slopes, calculating slopes, and being able to determine if slopes are parallel and perpendicular. Along in this section, there should be a practice for you to work on, actually testing to see if two given lines are parallel and perpendicular. If you have any questions or any comments on the video, feel free to shoot me an email. My email is klinford@wccnet.edu. Let me know what you think of the video and if you have any questions. Otherwise, I will see you in the next section.